Today our lecture about relativistic covariance of Dirac equation. The Dirac equation is Lorentz invariant. By this it means that the physics expressed by the independent of the Lorentz frame that is used. So the Dirac equation to recall is I gamma mu del mu minus m psi of x equal to 0. This is equation number 1. For a free particle corresponding the solution of the above equation, let us dwell into its property under the Lorentz transformation. This will help us to see the behavior of the 4x1 column vector psi of x. Under Lorentz transformation, we know that x mu prime equal to lambda mu nu x nu. The invariance of x mu implies lambda nu mu lambda mu sigma equal to delta nu sigma, or lambda transpose lambda equal to I. This is equation number 2 and this is 3. From which it follows lambda transpose z lambda equal to z. Congruent transformation by the lambda leaves the metric is unchanged. The Lorentz group. The Lorentz group is defined as group of the linear coordinate transformation of this equation, leaving invariance x mu are invariant. The Lorentz group is O 3,1, orthogonal 3,1. It is the non-compact group. We have seen above that G equal to lambda transpose Z lambda. Taking the determinant of this, we have determinant of lambda also equal to 1, or determinant lambda equal to plus minus 1. The transformation with determinant lambda equal to 1 are called proper Lorentz transformation, and the subgroup of O 3,1, and determinant of lambda equal to 1 is denoted by SO 3,1, special orthogonal 3,1, 3 space dimension 1 time dimension. Transformation with determinant lambda equal to minus 1 are called improper Lorentz transformation. This is improper Lorentz transformation. Can be written as product of the proper Lorentz transformation with the discrete transformation like parity, time reversal. The relation G equal to lambda transpose Z lambda written explicitly is G mu nu equal to G rho sigma lambda rho mu lambda sigma mu. In this, setting mu and nu equal to 0, we have G00 equal to 1 equal to G rho sigma lambda rho 0 lambda sigma 0, and G00 lambda 00 lambda 0 plus Gij lambda I0 lambda J0, and lambda 00 whole square minus lambda I0 whole square, so that lambda 00 whole square greater than equal to 1. Thus proper Lorentz transformation has two parts, with lambda 00 greater than equal to 1 and another part is lambda 00 less than equal to minus 1. These are called orthochronous or non-orthochronous respectively. This is orthochronous and this is non-orthochronous respectively. We will consider only proper orthochronous Lorentz group. It is continuous group. Consider an infinitesimal transformation like lambda mu nu equal to delta mu nu plus lambda mu nu, where lambda mu nu as infinitesimal. Substituting this in the G mu nu and G rho sigma lambda rho mu and lambda sigma nu. We have G mu nu equal to G rho sigma delta rho mu plus lambda rho mu delta sigma nu plus lambda sigma nu, and we have G rho sigma delta rho mu delta sigma nu plus delta rho mu lambda sigma nu plus delta sigma nu lambda rho mu, and we have G mu nu plus G mu sigma lambda sigma nu plus G rho nu lambda rho mu, and G mu nu plus lambda mu nu plus lambda nu mu, implying for the infinitesimal lambda mu nu equal to minus lambda nu mu. This is equation number 6. This is equation number 5. Since an antisymmetric 4x4 matrix has 6 independent elements, the Lorentz group has 6 parameters. They are 3 rotation angle, keeping t unchanged, and the 3 component of the relative velocity. There are 6 generators for the Lorentz group associated with the 6 parameter denote the 6 generator by the J mu nu equal to minus J nu mu. There an element of the Lorentz group is given by lambda equal to e to the power minus I by 2 lambda prime mu nu J mu nu, while lambda prime mu nu stand for parameters. The above expression on the representation we are using. For example, in the case 4 vector representation is J mu nu rho sigma equal to I G mu rho delta nu sigma minus G nu rho delta mu sigma. This is question number 8. An example, let us consider the homogeneous Lorentz transformation x1 prime equal to gamma x1 minus beta x0, x prime 2 equal to x2, and x prime 3 equal to x3, and x prime 0 equal to gamma x0 minus beta x1, where beta equal to v by c and gamma equal to root under 1 minus beta square. The above transformation can be written as x prime 0 equal to x0 cos hyperbolic q minus x1 sin hyperbolic q, and x prime 1 equal to x1 cos hyperbolic q minus x naught sin hyperbolic q, with tan hyperbolic q equal to beta and sin hyperbolic u equal to gamma beta and cos hyperbolic q equal to gamma. So this is equation number 9. For the above transformation, lambda mu nu equal to cos hyperbolic q minus sin hyperbolic q 0 0 minus sin hyperbolic q cos hyperbolic q 0 0 0 0 1 0 0 0 0 1. This is equation number 10. Now we consider the infinitesimal version of this by taking u very small, then using cos hyperbolic tends to 1 and sin hyperbolic tends to u. Then we find lambda mu nu equal to 0 minus u 0 0 minus u 0 0 0 0 0 0 0 0 0 0 0. And from this it is seen using lambda mu nu equal to g mu rho lambda rho nu, that lambda mu nu equal to u 0 minus 1 0 0, this is 1 0 0 0 0 0 and otherwise 0. This is equation number 12. And so lambda prime 1 0 equal to u. Using 3.7 using 3, 7 and 8, it is seen that lambda equal to the power minus I by 2 lambda prime mu nu j mu nu equal to the power u into I, with I equal to 0 minus 1 minus 1 0 0 0 0 0 and otherwise 0. And I satisfies that I square equal to 1 0 0 0 0 1 0 0 0 0 0 0 0 0 0 and iq equal to I. This is equation number 14. This is equation number 13. This is using 13, 14 and we recovered the equation number 10. So far we have been seeing how Lorentz group act on the 4-vector representation. Now we take up how it acts on the psi or a spinor. The solution of the psi of the Dirac equation, the one equation, is a 4-component column vector or spinor, and this is under equation number 2 Lorentz transform as psi of x psi prime of x prime equal to s of lambda psi of x equal to s of lambda psi of lambda inverse x prime. This is equation number 15, where s of lambda is 4 cross 4 non-singular matrix. What else it could be? We can see that the form invariance of the Dirac equation means that the Dirac equation is in given Lorentz frame, then in turns from the frame psi prime of x prime, which is satisfied I gamma mu del mu prime minus m psi prime x prime equal to 0. This is equation number 16, where del prime mu equal to del by del x prime mu. Now we can written as del by del x mu equal to del x prime mu divided del x mu del by del x prime mu equal to lambda nu mu del prime mu. This is equation number 17. Using equation number 2 and equation number 1, we can be written as I gamma mu lambda nu mu del prime nu minus m s inverse of lambda psi prime x prime equal to 0. This is equation number 18, where psi of x can be written as s inverse of lambda psi prime x prime. Multiplying the above equation by the s of lambda from the left, we find that I s of lambda lambda nu mu gamma mu s inverse of lambda del prime nu psi prime x prime minus m psi prime x prime equal to 0. Comparing this with the transform as equation number 16, the form invariance of the Dirac equation, which is satisfied if s lambda lambda nu mu gamma mu s inverse of lambda equal to gamma nu. That is s inverse of lambda gamma nu s of lambda lambda nu mu gamma mu equal to gamma prime nu. Say this is equation number 21 and this is equation number 20. We have seen equation from the equation number 15. The gamma matrices satisfied the fundamental relation gamma mu gamma nu plus gamma mu equal to 2 g mu nu. It is seen that equation number 3, that can be written as gamma prime nu plus gamma prime mu equal to 2 g mu nu. We invoke the Pauli's fundamental theorem, which states that given two states of the gamma matrices gamma mu and gamma prime mu, such that gamma nu plus gamma mu equal to 2 g mu nu, and otherwise this is so there can be exist a non-singular matrix S, so that gamma mu equal to S gamma mu S inverse. Demonstration of the Pauli theorem. Demonstration of Pauli theorem. Demonstration of Pauli's theorem. The above theorem is demonstrated by observing that any product of the several gamma matrices can be found in following 16 matrices, which is 4 cross 4 matrices, denoted by gamma A, where A stand for 1 to 16. They are I gamma 1, I gamma 2, I gamma 3 gamma 0, I gamma 2 gamma 3, I gamma 3 gamma 1, I gamma 1 gamma 2, gamma 0 gamma 1, gamma 0 gamma 2, gamma 0 gamma 3, I gamma 0 gamma 2 gamma 3, I gamma 0 gamma 1 gamma 3, I gamma 0 gamma 2 gamma 2, gamma 1 gamma 2 gamma 3, and I gamma 0 gamma 1 gamma 2 gamma 3, which is defined as gamma 5. Note that we are using the metric convention G00 equal to minus G11 equal to minus G22 equal to minus G33 equal to 1. It can be follows, this is equation number 26, this is equation number 25. It follows that gamma 0 whole square equal to 1, gamma 1 whole square equal to minus 1, gamma 2 whole square equal to minus 1, and gamma 3 whole square equal to minus 1. This is equation number 27. In addition, recall gamma nu equal to minus gamma nu gamma mu for mu not equal to nu, which is equation number 28. In the equation number 25, beside the 4 gamma matrices gamma 0, 1, 2, 3, we have introduced the 5th gamma matrices gamma 5 equal to I, gamma 0, gamma 1, gamma 2, gamma 3. The 5th gamma matrix plays very important role in particle physics relating to chiral symmetry and the mathematical physics for mathematics in the index theorem for Dirac operator. The properties of the 16 gamma matrices gamma A, equation of 25 can be written as A, all gamma A except I are traceless. All gamma A's except I are traceless. Option B, gamma A square equal to I for all A, and consequently gamma A inverse equal to gamma A, and the determinant is unity. If we multiply each gamma A on the left by any one of the Dirac matrices, then we obtain element of the set of 16 matrices that can be written as gamma B gamma C equal to omega C gamma C. With no summation over C, omega C plus minus 1 and plus minus I. Taking inverse of the above equation, option B can be written as gamma A gamma B equal to omega C inverse gamma C, and E, all gamma A are Hermitian. Gamma A are Hermitian. And if the gamma A are linearly independent, this can be proved easily. If gamma A are linearly dependent, then sigma A BA gamma A equal to 0. With not all BA is 0, multiplying by the gamma B, we have BA gamma B gamma A equal to 0 in the sum over A. This is sum over. In the sum over A, we isolate A equal to B and use for gamma A whole square equal to I and consequently gamma A inverse equal to gamma M to obtain BB plus which summation A not equal to B, BA gamma B gamma A equal to 0. That can be written as BB plus summation of A not equal to B, BA omega C gamma C equal to 0 using the arrangement D, and taking the trace of the equation using A, which A equal to B, then term is isolated and gamma C will not contain I, then find BB equal to 0, and option G. And the G property assumes any 4x4 matrices can be expanded in terms of gamma A, where n 4x4 equal to summation A gamma A, with A equal to 1/4 trace of gamma A n. The two set of gamma matrices satisfy equation number 23. There are gamma S and the gamma prime S are respectively. Let S in the equation number 24 can be written as S equal to summation J equal to 1 to 16 F prime J F gamma J, where F is an arbitrary 4x4 matrix. This is equation number 32. The above form can be understood by noting that S is 4x4 matrix, and so that from the property G can be expanded in terms of the gamma A also. S in 24 led to the gamma mu and gamma prime mu, so can we expand in terms of gamma prime M? The above encompasses these features, and for particular I, we left multiplying by equation number 32 by gamma I prime and right multiply to gamma I, and we can get gamma prime I is gamma I equal to gamma prime I summation of J equal to 1 to 16 gamma prime J F gamma J gamma I equal to summation J equal to 1 to 16 gamma prime I gamma prime J F gamma J gamma I. This is equation number 33. Using the property D, this can be written as gamma prime I is gamma I equal to K equal to 1 to 16 gamma prime K F gamma K equal to S. This is equation number 34. So gamma prime I S equal to S gamma I. So using the property B, we can written as gamma prime I equal to S gamma I S inverse. This is equation number 35, which verifies equation number 24 and 25. What is the role of the matrix F in equation number 32? The arbitrary matrix F in equation number 32 can be chosen so that S is not non-singular. Can we do that? First of all, F can be chosen so that S not equal to 0. If S equal to 0, then equation number 32 we have summation J equal to 1 to 16 gamma prime J F gamma J equal to 0. This is 36. Now as F is arbitrary, we take F to have only one element non-zero, say F mu nu equal to delta mu 0 and delta nu 0, where mu 0 denoted arbitrary index pair. Then the above expression is summation J equal to 1 to 16 gamma prime J rho mu F mu nu gamma J nu sigma equal to 0. So we can written as J equal to 1 to 16 gamma prime J rho mu 0 gamma J nu 0 sigma equal to 0. This is equation number 37. Therefore gamma prime J rho mu 0 gamma J equal to 0. Since nu 0 is arbitrary, and so taking all nu 0 and sigma, this contradict the property of F, property number F. For the particular choice rho and mu 0, so F can be chosen given by S is not equal to 0. Second, let us construct S prime equal to 1 to 16 gamma I G gamma prime I, 38, where G is arbitrary. By similar reasoning G can be chosen as so that S prime not equal to 0. By the step which lead to the equation number 34, we can find gamma I S prime, gamma prime I equal to S prime. This is equation number 39. From equation number 34 and 39, using the property B, we have gamma prime I S equal to S gamma I, and gamma prime I S prime equal to S prime gamma prime I. Right, multiplying by the S, and the second equation gives gamma I S prime S equal to S prime gamma prime I equal to S, so that S prime is gamma I. Using the first equation, we find that gamma I S prime S equal to 0 for all I equal to 1 to 16. This is equation number 40. Since only the unit 4x4 matrix commute with the all the 16 gamma A, we have S prime S equal to Ki, where K is a constant. Third, so that K not equal to 0, then S prime S equal to Ki. We have S prime I equal to 1 to 16 gamma prime I F gamma I equal to Ki. This is equation number 41. If K were 0, then we have is equal to 1 to 16 S prime gamma prime I F gamma I equal to 0. This is equation number 42. Once again, choosing arbitrary 4x4 matrix F as F mu nu equal to delta mu mu 0 and delta nu nu 0, the above expression lead to that summation I equal to 1 to 16 S prime gamma prime I rho mu 0 gamma I equal to 0. This is equation number 43, which contradict the property F. So K not equal to 0, then S prime F equal to Ki, so that S inverse exists and so that S is non-singular. This is complete demonstration of the fundamental theorem of Pauli from the equation number 21 and 24 by identifying S of lambda equal to S inverse, so that the Lorentz covariance of the Dirac equation is proved. Explicit expression for the S of lambda. S of lambda explicit expression. An explicit expression for S of lambda can be obtained from the equation number 21. We will stick to operator orthochronous homogeneous Lorentz transformation, which is determinate lambda equal to 1 and lambda 0 0 greater than equal to 1. For infinitesimal Lorentz transformation, we have lambda mu nu approximately delta mu nu plus epsilon lambda mu nu, which is lambda mu nu equal to minus lambda mu nu. This is equation number 44. From the equation number 2 and 44, we have x prime mu equal to x mu plus epsilon lambda mu nu x nu. So S of lambda to first order in the epsilon is written as S of lambda equal to I plus epsilon t, say, and S inverse of lambda equal to I minus epsilon t. This is equation number 40. Substituting 45 in 21 and using 44, we have I minus epsilon t gamma nu I plus epsilon t equal to gamma nu plus epsilon lambda nu mu gamma mu, that is gamma nu t minus t gamma nu equal to lambda nu mu gamma mu. This is equation number 46. A choice t equal to 1 by 8 lambda mu nu gamma nu minus gamma nu gamma mu. This is equation number 47, which is satisfied the equation number 46. Recall equation number 37. Earlier we have introduced sigma mu nu I by 2 gamma mu gamma nu. Therefore it can be written as, the 47 equation can be written as t equal to minus I by 4 sigma mu nu lambda mu nu. This is equation number 48. So that S of lambda equal to I minus I by 4 sigma mu nu lambda mu nu. This is equation number 49. absorbing the infinitesimal parameter epsilon in lambda mu nu from this finite transformation is found to be s of lambda equal to e to the power minus I by 4 sigma mu nu lambda mu nu. This is number 15. It follows from equation number 50 gamma 0 s dagger gamma 0 equal to s inverse and s gamma 0 s dagger equal to gamma 0. This is equation number 51. This can be verified as below. First, sigma mu nu lambda mu nu equal to 2 sigma 0 I lambda 0 I plus sigma ij lambda ij for I not equal to j. Then sigma 0 I equal to I gamma 0 gamma I and sigma ij equal to I gamma j. Therefore, s of lambda equal to e to the power minus I by 4 2 sigma 0 I lambda 0 I plus sigma ij lambda ij equal to e to the power 1 by 4 2 gamma 0 gamma I lambda 0 I plus gamma j lambda ij. This is equation number 52. Using the hermiticity property of the gamma matrices equation number, so we have s of lambda dagger equal to e to the power 1 by 4 2 gamma 0 gamma I lambda 0 I minus gamma j lambda ij. This is equation number 53. Now expanding the exponential, consider gamma 0 s dagger gamma 0 as gamma 0 s dagger gamma 0 equal to gamma 0 1 plus 1 by 4 2 gamma 0 gamma I lambda 0 I minus gamma j lambda ij plus 1 by 2 factor 1 by 4 whole square 2 gamma 0 gamma I lambda 0 I minus gamma j lambda ij 2 gamma 0 gamma m lambda 0 m minus gamma l gamma n lambda ln plus 1 by 3 factor 1 by 4 whole cube 2 gamma 0 gamma I lambda 0 I minus gamma j lambda ij 2 gamma 0 gamma m lambda 0 m minus gamma l gamma n lambda ln 2 gamma 0 gamma p lambda 0 p minus gamma p gamma q lambda p q plus gamma 0. Now using gamma gamma 0 equal to minus gamma 0 gamma I and gamma gamma j gamma 0 equal to gamma 0 gamma gamma j. Hence I not equal to j. So we have gamma 0 s dagger gamma 0 equal to gamma 0 plus 1 by 4 minus 2 gamma 0 gamma I lambda 0 I minus gamma 0 gamma I gamma j lambda ij plus 1 by 2 factor 1 by 4 whole square equal to 2 gamma 0 gamma I lambda 0 I minus gamma j lambda ij minus 2 gamma 0 gamma m lambda 0 m minus gamma 0 gamma l gamma n lambda ln plus 1 by 3 factor 1 by 4 whole cube 2 gamma 0 gamma I lambda 0 I minus gamma j lambda ij 2 gamma 0 gamma m lambda 0 m minus gamma l gamma n lambda ln equal to minus 2 gamma 0 gamma p lambda 0 p minus gamma 0 gamma p gamma q lambda pq plus as so on. So that can be written as equal to gamma 0 minus 1 by 4 gamma 0 2 gamma 0 gamma I lambda 0 I plus gamma gamma j lambda ij plus 1 by 2 factor 1 by 4 whole square gamma 0 whole square 2 gamma 0 gamma I lambda 0 I plus gamma I gamma j lambda ij 2 gamma 0 gamma m lambda 0 m plus gamma l gamma n lambda ln minus 1 by 3 factor 1 by 4 whole cube gamma 0 2 gamma 0 gamma I lambda 0 I plus gamma I gamma j lambda ij whole cube plus as so on. That can be written as e to the power minus 1 by 4 2 gamma 0 gamma I lambda 0 I plus gamma I gamma j lambda ij equal to a sub lambda inverse. So this is equation number 55. An immediate consequence of equation number 51 to show that Dirac current J mu equal to psi tilde gamma mu psi transform like as a 4 vector under Lorentz transformation when psi of x goes to psi prime of x prime equal to a sub lambda psi of x under Lorentz transformation psi tilde of x goes to psi tilde of x prime which is psi tilde prime of x prime equal to psi prime dagger gamma 0 and a sub lambda psi of x dagger gamma 0 equal to psi dagger x s dagger of lambda gamma 0 and psi dagger gamma 0 s dagger of lambda gamma 0 equal to psi tilde of x s inverse of lambda. This is equation number 56 where we use the definition psi tilde equal to psi dagger gamma 0 and gamma 0 also equal to I. So the equation of 51 or 55, then we ask the task j mu nu of x equal to psi tilde of x gamma mu psi of x under Lorentz transformation j mu of x which is j prime mu of x prime equal to psi tilde prime of x gamma mu psi prime of x prime. So this is equation number 57. From equation number 15 and 56 we can find j tilde mu of x which is j prime mu of x prime equal to psi tilde of x s inverse of lambda gamma mu s of lambda psi of x. This is equation number 58. So equation number 21 can be written as j mu of x which is j prime mu of x prime equal to psi tilde of x lambda mu nu gamma nu psi of x equal to lambda mu nu j nu of x. This is equation number 59. Showing the desired transformation of j mu as a covariant 4 vector. From the transformation property j mu is follows j0 will transform like a 4 component of a 4 vector and j0 of x equal to psi dagger of x psi of x. The combination psi dagger of x and psi of x cannot be served as good normalization of the psi of x as combination is not Lorentz invariant. It is easy to see that combination of psi tilde and psi is invariant under Lorentz transformation so an invariant normalization will be provided by psi tilde and psi. Discrete transformation of the psi of x, the parity. So a space reflection can be affected by x mu which is x prime mu equal to lambda mu nu x nu while lambda mu nu equal to 1 minus 1 minus 1 minus 1 otherwise 0. This is equation number 60 and this is equation number 61. And determinant of lambda equal to minus 1 under space reflection let psi of x change to psi prime of x prime which is a sub lambda psi of x where now this is a sub lambda is not the same as the case of the proper Lorentz transformation. The form invariance of the Dirac equation under parity we have s inverse of lambda gamma nu a sub lambda equal to lambda nu mu gamma mu. This is equation number 62 which reads that S inverse of lambda gamma 0 S of lambda equal to gamma 0, and gamma 0 S of lambda equal to 0, and S inverse of lambda gamma I S of lambda equal to minus gamma I, and gamma I S of lambda equal to 0. This is equation number 63, where we denote anti-commutator AB plus BA by A comma B, a choice S of lambda equal to eta gamma 0. This is number 64, which is satisfies equation number 63. In here, eta is arbitrary phase and mod eta whole square equal to 1. Thus, the under parity transformation, psi of x, which is psi prime of x prime equal to psi prime of minus x vector t equal to eta gamma 0 psi of x. This is equation number 65. Transform of the psi tilde of x follows from the above. Psi tilde of x, which is psi tilde prime of x prime equal to psi prime dagger of x prime and gamma 0 x prime and gamma 0, which is eta gamma 0 psi of x dagger gamma 0, which is eta star psi tilde of x gamma 0. Transform properties of psi of x and psi tilde of x under Lorentz transformation and the parity can be used to determine the following bilinear form, which is psi tilde and psi of x. The remain unchanged under Lorentz transformation can be also under parity. This is the bilinear, this is a scalar, and from this is a scalar, psi tilde of x and psi tilde, this is a scalar. Then second, psi tilde of gamma mu psi of x, so that can be transformed as eta square psi tilde of x gamma 0 gamma mu gamma 0 psi of x, which is psi tilde of x gamma 0 psi of x and minus psi tilde of x gamma I psi of x, which is 67, and psi tilde of x gamma nu psi of x is a vector. This is a scalar. And the third, psi tilde of x gamma phi psi of x. This is so. This is remain unchanged under Lorentz transformation using gamma phi S of lambda, which is anti-commutator is 0 under parity. So under parity, psi tilde of x gamma phi psi of x, which is eta square psi tilde of x gamma 0 gamma phi gamma 0 psi of x, which is minus psi tilde of x gamma phi psi of x. This is a pseudo scalar. Transform as like pseudo scalar. Pseudo scalar. This is scalar. The sign change, which is pseudo scalar. The time component change, then pseudo scalar. Then the fifth is psi tilde gamma phi gamma mu of psi. So this is a pseudo vector or axial vector. You can check that. This is pseudo vector or axial vector. Now option B, psi tilde of x sigma mu nu psi of x. Under Lorentz transformation, psi tilde of x S inverse sigma mu nu S of lambda psi of x, which is psi tilde of x S inverse of lambda gamma nu minus gamma mu S of lambda psi of x I by 2. Equal to psi tilde of x S inverse of lambda gamma mu S of lambda S inverse of lambda gamma nu S of lambda minus S inverse of lambda gamma nu S of lambda S inverse of lambda gamma mu S of lambda psi of x I by 2 equal to lambda mu sigma lambda nu rho psi tilde of x sigma rho psi of x. This is equation number 70. Where in the last step, equation number 62, this follows that psi tilde of x sigma mu nu psi of x transform as the second rank contravariant tensor under Lorentz transformation under parity. This is a tensor which is minus psi tilde of x sigma I0 psi of x and psi tilde of x sigma ij psi of x. Now property number 6, psi tilde gamma 5 sigma mu nu psi of x. Under Lorentz transformation, this is a pseudo tensor which is transformed like as psi tilde. You can check that sigma I0, this equation, this property like 5 minus psi tilde of x gamma 5 sigma ij psi of x. This is question number 72. This is pseudo tensor. Now 7. Now psi tilde of x q mu psi of x. So as q mu is the 4 momentum. Under Lorentz transformation, this is psi tilde of x s inverse of lambda lambda mu nu q nu s of lambda psi of x, which is lambda mu nu psi tilde of x q nu psi of x. This is 73. Transform as 4 vector under parity. The spatial component of the 4 momentum change the sign. This is a vector. Bilinear is a vector. This bilinear is a vector. Now this is the 8, psi tilde of x gamma 5 q mu psi of x. Under Lorentz transformation, this is a pseudo vector or axial vector. And property number 9, psi tilde q mu sigma mu nu psi, which is a vector. Which is a vector. So psi tilde q mu sigma mu nu psi of x, which transform like psi tilde of x s inverse of lambda rho mu q rho sigma mu nu s of lambda psi of x, which is lambda rho mu lambda mu alpha lambda nu beta psi tilde of x q rho sigma alpha beta psi of x equal to lambda nu beta psi tilde of x q alpha sigma alpha beta psi of x. This is question number 77. So from the step number 5, we show that psi tilde q mu sigma mu nu psi of x transform is a 4 vector under Lorentz transformation. To find transformation under parity, denote q mu sigma mu nu by q nu. So psi tilde q0 psi of x, where q mu sigma mu nu equal to q nu, this denote, which is psi tilde of x qi sigma I0 psi of x, and show that psi tilde of x qi sigma I0 psi of x, which is psi tilde of x gamma 0 minus iqi sigma I0 gamma 0 psi of x, which is psi tilde q0 psi. This is question number 78. Using sigma I0 equal to I gamma 0, so that Second, psi tilde of x qi psi of x equal to psi tilde of x q0 sigma 0 I plus qj sigma ij psi. And under parity, psi tilde of x qi psi of x, which is psi tilde of x gamma 0 q0 sigma 0 I gamma 0 plus gamma 0 minus qj sigma ji gamma 0 psi of x, which is minus psi tilde of x qi psi of x, using gamma ij equal to I gamma j. Thus psi tilde of x q nu psi of x, which tends to psi tilde of x q0 psi of x minus psi tilde of x qi psi of x, which is a vector. Now the bilinear property x, 10 bilinear property number 10, gamma 5 q mu sigma mu nu psi of x. So this is axial vector. You can show that. So we now make, this is equation number 82. We now make two important remark. First Dirac equation I gamma mu del mu minus m psi equal to 0 is I gamma 0 del 0 plus I gamma I del I minus m psi equal to 0. Under parity operation is transformed like that: I gamma 0 del 0 minus I gamma I del I minus m eta gamma 0 psi equal to 0, which is eta gamma 0 I gamma 0 del 0 plus I gamma I del I minus m psi equal to 0, which is 0. Hence the Dirac equation respect parity expected 62. Equation number 62. Consider the Dirac equation, the left multiplying by the gamma 5 and using the relation gamma 5 and gamma mu equal to 0, anticommutative relation. Then we find the equation I gamma mu del mu plus m gamma 5 psi equal to 0, I gamma mu del mu plus m gamma 5 psi equal to 0. This means that if psi satisfied the Dirac equation, then gamma 5 psi, which is the Dirac equation, replaced by mass of minus m, which is gamma 5 psi, then we can replace mass to the minus m. This means massless particle, both psi and gamma 5 psi satisfy the same equation. For massless particle, then this is 0, then gamma 5 psi and psi, this both spinner which is satisfied the same equation. Now the time reversal. The time reversal decomposition. The time reversal operation. The time reversal transformation similar to the parity operation implemented by x mu, which is x prime mu, which is lambda mu nu x nu. And lambda with lambda mu nu equal to minus 1 1 1 1, and determinate lambda equal to minus 1. This is equation number 84 and this is equation number 83. If psi of x change under time reversal to psi prime of x prime, then we know that psi prime of x prime equal to s of lambda psi of x, which is number 85. Now lambda given by equation number 84 by the 21 equation, s lambda, which is satisfies s inverse of lambda gamma nu s of lambda equal to lambda mu nu gamma mu, which is equation number 86. This gives s inverse of lambda gamma 0 s of lambda equal to minus gamma 0, and s inverse of lambda gamma I s of lambda equal to gamma I, which is equation number 87. A choice s of lambda equal to eta prime gamma 5 gamma 0, which is equation number 88. So we choose the S of lambda like that, and has eta prime mod square equal to 1. If we consider the Dirac equation, I del mu I gamma mu del mu I gamma mu del mu minus m psi equal to I gamma 0 del 0 plus I gamma I del I minus m psi equal to 0. Under time reversal, this becomes minus I gamma 0 del 0 plus I gamma I del I minus m, which is eta prime gamma 5 gamma 0 psi. Using the anti-commutating relation of the gamma matrices, this can become eta prime gamma 5 gamma 0 I gamma 0 del 0 plus I gamma I del I minus m psi, which is satisfied to 0. Now the charge conjugation. We shall consider the Dirac equation in an external electromagnetic field to bring out the meaning charge conjugation. For an electron interaction giving the vector potential a mu, we can correspond to the Dirac equation I gamma mu del mu minus m psi equal to E gamma mu a of x psi of x, which can be written as I gamma 0 del 0 plus I gamma I del I minus m psi of x equal to E gamma 0 a0 of x plus gamma I ai of x equal to psi. Taking, this is 89. Taking the Hermitian conjugate, we get minus I del 0 psi dagger gamma 0 plus I del I psi dagger gamma I minus m psi dagger equal to E psi dagger a0 gamma 0 minus ai gamma I. We used gamma 0 dagger equal to gamma 0, which is Hermitian, and gamma I dagger equal to gamma minus gamma, which is anti-Hermitian. Multiplying now right multiplying by gamma 0, we have minus I del 0 psi tilde gamma 0 minus I del I psi tilde gamma I minus m psi tilde, which can be written as E psi tilde a0 gamma 0 plus ai gamma I. So we have I del mu psi tilde gamma mu plus m psi tilde equal to minus E psi tilde gamma mu a mu, which is equation number 91. Taking transpose of the equation, above equation, and we have I gamma mu transpose del mu psi tilde transpose plus m psi tilde transpose equal to minus I gamma mu transpose a mu psi tilde transpose. This is equation number 92. If we can find non-singular 4x4 matrix C such that gamma mu transpose equal to minus C inverse gamma mu C equals, this is equation number 93, then equation number 92 can be written as minus I C inverse gamma mu C del mu psi tilde transpose plus m psi tilde transpose equal to C E C inverse gamma mu C a mu psi tilde transpose. This is equation number 94, which upon multiplying C from the left becomes minus I gamma mu del mu C psi tilde transpose plus m C psi tilde transpose equal to E gamma mu a mu C psi tilde transpose, which can be written as I gamma mu del mu minus m C psi tilde transpose equal to minus E gamma mu a mu C psi tilde transpose. This is equation number 95. If equation number 89 described as electron is negative in electron charge is minus C interacting with the electromagnetic field with the a mu vector field, then 95 equation describe the spin half particle of the charge plus C interacting with the electromagnetic field a mu, which can the wave function C psi tilde transpose This is the both have the same mass. A matrix is satisfy 93 equation can be taken to be C equal to eta double prime gamma 2 gamma 0 and C inverse equal to minus eta double prime gamma 0 gamma 2 and C dagger equal to minus eta double prime star, which is complex conjugate, gamma 0 gamma 2. This is equation 96. Okay. Now the Gödel decomposition, Gordon decomposition, we have used equation we have shown the equation in equation of 59 that can be current J mu of x, which can be written as psi tilde of x gamma mu psi of x transforms like the 4 vector under Lorentz transformation. Consider the Dirac equation for a free particle with the positive energy, then write psi of x equal to u of p e to the power minus ipx. It is seen that the equation u of p is p slash minus m u of p equal to 0, which is the equation of psi tilde of x. So we can find u tilde p slash minus m equal to 0. Consider the two spinner u of p and u of q is satisfying the above equation p and q respectively. Consider u tilde of p sigma mu nu p minus q u of q. Using the equation of 15 can be shown that sigma mu nu p minus q nu equal to I p mu plus q mu minus p slash gamma mu minus gamma mu q slash. This is equation of 116. Equation of something. So that u tilde of p gamma mu u of q can be written as 1 by 2m u tilde of p mu plus q mu u of q plus I by 2m u tilde of p sigma mu nu p minus q u of q. The above decomposition, which is known as Gordon decomposition, which is split the Dirac current into two parts. First, not involving gamma matrices representation, the convection piece, and the second is the spin piece. We conclude the we conclude this lecture chapter by the examining the spinor representation in the Lorentz group. Okay. Now equation number 8 can be seen that J mu nu and J rho sigma equal to I G nu rho J mu sigma minus G mu rho J nu sigma minus G nu sigma J mu rho plus G mu sigma J nu rho, which is equation number something. Giving the Lie algebra of SO 3,1, special unitary of 3,1, if we arrange the component of J mu nu, that can be written as Ji equal to 1 by 2 epsilon I j k where ki equal to j I0, which can be defined as j vector plus minus equal to 1 by 2 j vector plus minus I k vector. That can be find that j plus I and j plus j equal to I epsilon I j k j plus k, and j minus I j minus j equal to I epsilon I j k j minus k, and j plus I and j minus j equal to 0. Thus we obtain two copies of SU2 algebra commuting between themselves. Lorentz algebra can thus be written as the algebra SU2 cross SU2 cross SU2. The state transforming in a well-defined way will label by j and j prime corresponding to the Casimir of each piece. Then j0, which corresponding j vector equal to I k vector, and 0j, which corresponding j vector equal to minus I k vector. as k involves the Lorentz boost under parity k prime equal to minus k prime, and so that J0, which is 0j. For spin half particle we have 1 by 2 0 and 0 1 by 2 spinor, both have dimension 2, called left-handed and right-handed while spinor. The fourth spinor psi is an irreducible representation of the Lorentz group extended by the parity. So that is the whole concept. So thank you. Please like, share and subscribe.